Hey everybody, let's start combining resistors, inductors, and capacitors all in the same circuit. So let's start off with them in parallel, and then let's do a natural response, and then we can try out the step response, and then we can combine them in series, and then do natural response and step response. Okay, so let's start off. Let's say this switch is open, so then this current source has been feeding current this way for a long time. So this switch was open for a long time. What would happen? So if it's open for a long time, then the voltage would be constant, and then the current would be constant. So then what happens for a capacitor? The current through the capacitor looks like this. And then if the voltage is constant, then the time derivative would be 0. So the current through the capacitor would be 0, right after a long time. So there's no current going this way. For the inductor, the voltage looks like this. So if the current is constant, then the time derivative would be 0. So the voltage across here would be 0, which is like saying it's a short circuit, like a wire, which means it's hogging all of the current. The capacitor doesn't get any, the resistor doesn't get any. The inductor takes all the current. Okay, and then let's say at t equal to 0, we close this switch, which basically shorts out the current source. So it's like removing the current source at t equal to 0. Okay, so when that happens, we remove the current source. The inductor had all the current. What will happen now? So let's get rid of this, right? We short that out. What happens to these three? Okay, so they definitely all have the same voltage because they're in parallel. But then let's use KCL to figure out the current. KCL. So there's current here and here and here. So the current through the capacitor is C dV dt. The current through the inductor, I'm not sure. I know the voltage through the inductor looks like this. So if we want the current, let's move L over here on this side and then do separation of variables. So dI is 1 over L V dt, and then we can integrate like this. All right, so then I equals I naught plus 1 over L integral V dt. So this is the current through the inductor. I naught plus 1 over L V dt. And again, the initial current is all of this one, right? Because that inductor was hogging all of the current. Okay, now what's the current through a resistor? V over R. Okay, so there you go. There's KCL. Okay. I would like to not have this here, this integral. So here's a trick. Let's take a time derivative of the entire equation. So take a time derivative of everything. So time derivative of this, so C, right? So that'll be the second derivative. Time derivative of a constant is 0. 0, right? And then the derivative of an integral, those are inverses, so it'll just be 1 over L V. Time derivative of that, 1 over R dV dt. Okay, now let's take a look at this. Let me rewrite it. Let me divide everything by this coefficient over here, C over C. Okay, and then let me just rewrite it over here. in decreasing order of the derivative. Okay, now take a look at this. This is a homogeneous second order ODE with constant coefficients. Right? The highest degree, second order, highest order is second, and then, right, it's v dv dt, v squared. And so circuits like this are called second order circuits. Okay, how do we solve it? That's the thing. Now let me show you a shortcut for less writing. Whenever you have time derivatives, instead of writing like this, you can write it like this. This is only okay for time derivatives, right? So instead of dv dt, you just write v dot. Instead of second derivative like this, v double dot. It's just less writing. Okay, so you're free to use this notation from now on. And now how do we solve this? We just guess. What function, we're trying to solve for v as a function of time, right, the voltage. What function is proportional to its own first derivative and its own second derivative? Right, we need some function that satisfies this equation, where this plus this equals 0. So we can make a guess. A function that's proportional to its own derivatives is exponential function. So I'm just going to give some coefficient, e to the, like this. So for coefficients a and s, right? So this looks like some kind of exponential function like this. Right, exponential function. Take a derivative, same thing. Take another derivative, same thing. Okay, let me do that right now, right? What is v dot? S a e to the st. What is v double dot? S squared a e to the st, right? So then we can plug this in here, plug this in here. So let's substitute this into the ODE. What do we get? S squared, right here. A e to the st, and then plus 1 over RC v dot, which is this, S a e to the st, plus 1 over LC v, which is this, equals 0. Right? And then we can do some factoring a little bit. Okay, now let's take a look at this. Something times something equals 0. Now, this is definitely not 0, right? This is our voltage function. So that means this must be 0. That's called the zero product principle. Something times something equals 0. Means this equals 0 or this equals 0. Okay, so this must be 0. This is called something. This is called the characteristic equation. Because the roots of this equation will determine how the circuit behaves. Okay, so how do you solve for this? What is S? We can just use the quadratic formula. Okay, so the quadratic formula, let's say I have a quadratic equation that looks like this. Right? If the quadratic looks like this, the solution is like this. Okay, this is the quadratic formula. Okay, so then here, you see right here, I'm going to go, oh, it's 1 over RC. I'm going to factor 2. So like 2 over 2. Right, so then let me just do some substitutions. So let alpha equals whatever is right over here. So 1 over 2RC. And then I'll do another substitution. Square root of 1 over LC. Okay, so if I do these substitutions, the characteristic equation will turn into this. Right? If I do that substitution. Okay, and this is something called the Neper frequency. And this is called the undamped natural frequency. Okay, so sometimes called the undamped radian frequency. This is a more precise definition of it. Okay. So now let's use the quadratic formula to solve for the roots of our characteristic equation. So this would be negative alpha plus or minus square root of alpha squared minus omega naught squared. Okay, so we have the roots of our characteristic equation. And again, this was our guess right here for the voltage. So let me jot that down over here. Right, so V was supposed to be A e to the st. But look, there are two roots, minus alpha plus this, minus alpha minus this. But the thing is, there are some possibilities here, because depending on the values of R, L, and C, right, that will determine this frequency and this frequency. These are radians per second, the units, right? So based on the values of R, L, and C, this alpha might be larger than omega, it might be smaller, or they might be equal to each other. So we have three different possibilities. So possibility 1, let's say alpha is larger than this. What happens then? This would be positive, right? What happens if alpha equals omega? This would be 0, and then we would only have one root for a quadratic. We're supposed to have two roots for a quadratic, right? So that's called a repeated root. And then what happens if alpha is less than omega? Then look, this would be negative. So then you'd have a square root of a negative number, which means we would have two imaginary roots, right? So then here we would have two real roots. Here we would have a repeated root. And then here we would have two imaginary, well, complex roots, right? Okay, so then we have three different types of solutions depending on the values of R, L, and C. Okay, so let me go over those solutions in the next video. So I'll see you on that one.